in last lecture we have studied the dynamics of the single particle and dynamics of the system of the particles, in which we have studied laws of the conservation of a linear momentum, angular momentum and energy. Now in this lecture we are going to study how we can apply those laws in a day-to-day life or for any practical purpose. So in this lecture we are going to see how these conservation laws and the Newton's laws of motion are applied for the motion of the rocket. Though the motion of the rocket is a very complex phenomena, but still we are just going to deal with a simple basic laws which are used in the motion of the rocket. Okay, so this is the physical significance of the conservation laws to the motion of the rocket. This lecture will deal with the application of the conservation laws to the motion of the rocket. So let us see. Suppose this is a rocket. Consider the rocket with a mass m. So this is the initial mass at the time t is equal to 0, and v is the initial velocity of the rocket. So m is the initial mass and v is the initial velocity. And we know that for a particle or the system of the particles, if mass is m and v is the velocity, its momentum will be m into v. So this motion of the rocket is mainly based on Newton's third law, which says that every action has equal and opposite reaction due to the combustion of the fuel. Okay, so some fuel is combusted, and this combustion of the fuel will provide the upward thrust to the rocket. So motion of the rocket is mainly working on the Newton's third law, which says that every action has an equal and opposite reaction. So the amount of fuel which is burned in this rocket, which will provide the upward thrust to the motion of the rocket. Now suppose in time dt, dm is the mass reduced of the fuel. So dm is the reduced mass of a fuel, and dt is a time required to reduce this mass. And suppose due to the reduction of this mass delta m dm, so velocity will increase by the amount dv. So this is increase in velocity. So we can write at time t, let call the momentum as p1. So this pm will be m minus dm. So this is the remaining mass at time dt, and this v plus dv. So this is the increase in velocity at time dt. Therefore the momentum is nothing but mass into velocity. So at time dt, so the mass is m minus delta m and velocity is v plus delta v. Therefore p1 is the momentum at time dt. Now suppose this exhaust gas, it will also have some velocity, and let's call that velocity as u. So u is the velocity of the exhaust gas. So the gas is moving in a downward direction which is opposite to v. So therefore we have to consider this velocity as a minus u, and this momentum of this exhausting gas, let it consider as a p2. Momentum of the exhaust gas p2 will be dm into v minus u. So by using law of conservation of the linear momentum, we can write p is equal to p1 plus p2, and just put the values of p1. So p1 is m minus dm into v plus dv, and plus p2 is nothing but dm into v minus u. So let us solve this. So it will be mv plus mdv minus vdm minus dm dv. So plus vdm minus udm. So this p is nothing but m into v. So let us solve this. So this plus vdm and minus vdm, they will be cancelled out, and you can neglect this term because as compared to the mass of the rocket, so this change in mass or the reduced mass is very small, and change or the increase in velocity is also very small. So the multiplication of this dm into dv as compared to this m into v, that can be neglected. So what are the terms we are remaining with? So this is mv plus mdv minus udm. If I take this mdv on the left hand side, I can write mv minus mdv is equal to mv minus udm. As these two terms are equal, I can write mdv is equal to udm, or if I divide on the both sides by dt, I can write it as mdv upon dt is equal to udm upon dt. Now this is called as the equation of the motion for the rocket, and this right hand side is nothing but the upward thrust, which is given by udm upon dt. With this upward thrust created, so upward thrust means the force which is applied for the rocket for its upward motion, it is supplied by the u is the velocity of the exhaust gas, which is in a downward direction. So every action has equal and opposite reaction. So this is nothing but the u, and this is the upward thrust. So this combustion of this exhaust gas, this will generate exactly equal and opposite upward thrust. Okay, so this is how we can use laws of conservation of the linear momentum to derive the motion of the rocket. Similarly, the different laws of the conservation, like conservation of the angular momentum, conservation of the energy, so these laws can be used to calculate the motion of the different physical systems. Like we can use the laws of conservation to calculate the motion of a simple pendulum, compound pendulum. So these conservation laws are used in a classical mechanics, in quantum mechanics, even in statistical, thermodynamics. Everywhere these conservation laws are used to deduce the equation of the motion of the different physical systems.